Good evening, everyone. Thank you for being here. Welcome to UNSW. My name's Andrew Francis. I'm a professor of mathematics and head of the School of Maths and Stats here at UNSW. Very happy to have you all here today. We are on the lands of the Bedegal people of the Eora Nation, and I'd like to acknowledge their custodianship of these lands for tens of thousands of years and pay my respects to their elders, past, present, and any Indigenous people with us today. So it's a great pleasure to welcome Professor Karen Willcox here today. Karen is our 2024 UNSW Women in Mathematics and Statistics Ambassador. And she has quite a lovely bio here, which I'm going to have to read because it's too long for my poor mind. But before I forget, I would say that she is a member of the New Zealand Order of Merit, which is the most significant thing, of course, in all of this. So Professor Willcox is director of the Oden Institute for Computational Engineering and Sciences. She's Associate Vice President for Research and Professor of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. She's also External Professor at the Santa Fe Institute, and prior to joining the Oden Institute in 2018, she spent 17 years as a professor at the Massachusetts Institute of Technology, where she served as Professor of Aeronautics and Astronautics, the founding co-director of the MIT Center for Computational Engineering, and the associate head of the MIT Department of Aeronautics and Astronautics. Professor Willcox holds a Bachelor of Engineering degree from the University of Auckland, just a short step away, and a Master's and PhD degrees from MIT. Prior to becoming a professor at MIT, she worked at Boeing Phantom Works with the Blended Wing Body Aircraft Design Group. And I think we're going to hear a bit about aircraft design today. So it's a great pleasure to have Karen here to talk to us about digital twins and their applications across engineering, science, and medicine. Thank you.
All right. Thank you very much, Andrew, and it's really great to be here. I'd like to thank you all for braving the very New Zealand-like weather to come out tonight, and thank you to Francis for the invitation. It was really wonderful to be a part of the Do the Maths event yesterday and see so many, almost 500 young women coming and just seeing the incredible impact and all the careers ahead of them in math. So it's going to be hopefully fun and light today to see a little bit about digital twins. Francis kept telling me it's a public lecture. There'll be maybe high school students, parents, non-experts here, so you're not going to see, I don't think, any equations, but I hope I will give you a little bit of a sense of some of the technology that goes into digital twins and why it's so exciting. Okay, so we're going to start by going back into the past. So I'm going to take you back to the 1960s, 1970s, probably before most of us in the room were even born, to the Apollo program. And in the Apollo program, when NASA launched a spacecraft up into space, at the same time, they also launched a simulator that they kept on the ground in Houston. And the idea was that the simulator would follow along in the mission so that when the spacecraft's up in space, here you have the simulator on the ground following along. Now, this wasn't a digital simulator back then. This was a physical simulator, but a simulator nonetheless. So this practice became very important in the Apollo 13 mission. And I have to ask how many people here have seen the movie? Yeah, some. So especially to the young people here, if you haven't seen it, you should watch it. It's a really fantastic movie. So if you haven't seen the movie, I'm going to ruin the story for you a little bit. Apollo 13, the spacecraft suffered a malfunction and got badly damaged. And it basically got stuck up in space with the astronauts on board. And so now the story goes, and this is 1970s, the story goes that NASA were able to take the data from the physical spacecraft stranded up in space. So this is data from sensors on board, from observations that the astronauts are making. Take that data, feed it into the simulator on the ground in Houston, update the simulator so that now the simulator is a simulation of the damaged spacecraft, and now use that adapted simulator to run all the scenarios, to play all the what-ifs, and plan out the ways in which they could try to bring the astronauts back home safely. And I won't tell you how it ended if you haven't seen the movie. This is a great example back in 1970 where we see data. What do you Australians say? I have to say data. Data, models, in this case the model, a physical simulator, being put together in a way to really drive effective decision making. Okay, 1970. Let's come to the present. And now I want you to imagine that maybe you own an aircraft. This particular one, this is called a Telemaster. It's kind of a kit model. It's a big aircraft, about 20-foot wingspan that is remotely piloted. And I have one of these that my research group use for research. So I want you to imagine that you own some kind of an aircraft. And I want you to imagine that, again, your aircraft has sensors on board, that you could be collecting data about your aircraft every time it flies, and that you could be feeding that data into a model of your aircraft and using that model to make decisions about your particular aircraft. For example, you could imagine taking that model, and now when I'm talking about a model, I'm really talking about a computer model of your aircraft. You could imagine that model sort of following along in the digital world, so that when your aircraft flies, your digital model is experiencing the same kinds of conditions. And again, you're collecting data, feeding it in, and, for example, making decisions about when you might need to do maintenance on your aircraft. And then I want you to imagine that maybe you're an airline, or maybe one day you're Amazon and package delivery drones, and you own hundreds or thousands of these aircraft. And you could imagine that having one of these digital models for each one of those aircraft, each digital model following along its own aircraft, would be incredibly useful for you to drive decision making about things like predictive maintenance. And this is kind of a reality. This is the digital twin idea. This is a reality already today, where companies and the Air Force are using this idea to drive especially predictive maintenance for aircraft structures and for aircraft engines. Okay, so we've thought about the past, the Apollo example. This is a current example where we see digital twins in practice. Now I want you to think a little bit about the future in a completely different setting. So we're going to move away from aerospace engineering now. So what are we looking at here is radiotherapy regimens for high-grade gliomas. High-grade glioma is a particular kind of brain cancer. And what you see here is what's called the standard of care. So this is the standard treatment plan that's given to all patients. And what we're looking at here is a treatment plan after surgery. So after some surgery to cut away what part of the tumor they can. On day 0, this little blue dot here is an MRI, an image that's taken. Then there's a period of time post-surgery where the patient is really recovering from the surgery. Then on day 20, there's another image taken, and at that time the radiotherapy starts. And these little purple bars represent the days of radiotherapy, and each little purple bar is 2 grays per day. Gray is a measure of the dosage here, the radiotherapy dosage. So you get 2 grays per day on Monday, Tuesday, Wednesday, Thursday, and Friday. Then Saturday and Sunday, no treatment, and then 2 grays per day the next week, Monday, Tuesday, Wednesday, Thursday, Friday, for weeks 1, 2, 3, 4, 5, and 6. And again, that's the standard of care. Then at some point in the future, there's an assessment of what's called the time to progression. So with this particular kind of tumor, it's really about trying to delay how long until it comes back. So the time to progression, and then a follow-up observation. Okay, so now I want you to think about that Apollo example, and I want you to think about that example with the aircraft and the predictive maintenance. And now imagine that we could bring the same kind of thinking, that we could take the data especially from these images of the patient, that we could take that data, put it together with a model, a digital model of that patient's brain, their anatomy, their brain properties. I guess I could say some of us have more white or gray matter than others. Their particular tumor state, put all that together and use it to drive a patient-specific treatment plan. And I'll come back to this later in the talk, but again, just to sort of get you thinking, you could imagine in this patient-specific treatment plan, you're still imaging at day 0. From that image, you're now starting to create this personalized digital model of the particular patient. Again, at day 20, there's another image. For the first week, standard of care, 2 grays per day on Monday, Tuesday, Wednesday, Thursday, Friday. Then going into the second week, maybe you take another image with this third image. You could start to calibrate not just what's going on in the patient, but also how they are responding to the treatment. And now with this calibrated model targeted towards a specific patient, you could imagine now coming up with a patient-specific optimized treatment plan where you're varying the dosage according to what's going on with the particular patient. So again, this is a future vision. This is what the kind of thing that a digital twin could bring to medicine through patient-specific approaches. And this is something that we can't yet do today, but something that we're really trying to work towards. Okay, so what's the common theme across all 3 of these examples? We have models. In the Apollo example, the model was a physical simulator. If we fast forward now to the year 2024, we're very fortunate that we have incredible mathematical models that we can solve on today's supercomputers. So we have these incredible computational digital models. We have data. Again, if you think about 1970, the kinds of sensing technology that was available, and you think about what we have today in engineered systems, in medicine, in the natural world around us, we have many, many different kinds of data sources. We can put those 2 together. We can mathematically go through the process of data assimilation, which is taking data, interpreting it through the lens of the model, forming these personalized models and using it to drive predictions in support of decision making. And whether we're thinking about the medical setting, the brain cancer, the aircraft structural health monitoring, or that Apollo, this idea of the models and data driving better decisions is incredibly powerful. So this is really what we mean when we say a digital twin, and I've got a definition up here. There was a recent large study that I chaired, so this is a national level study by the National Academies in the US that has proposed this definition, really trying to think about digital twins, not for a particular use case, but spanning across all these different places in engineering, science, and medicine that we could imagine digital twins. So let's look at the definition. A digital twin is a set of virtual information constructs, so a virtual model, set of models, that mimics the structure, context, and behavior of a natural, engineered, or social system, or a system of systems, is dynamically updated with data from the physical twin, has a predictive capability, and informs decisions that realize value. The bidirectional interaction between the virtual and the physical is central to the digital twin. So it's really just a definition that sort of pulls together all the things I said with the examples. So let's think about the ingredients of the digital twin. So the first ingredient is the physical system. And I've given you examples from medicine. I've given you examples from engineered systems. But we could also think about building digital twins of the natural world around us. This image here is an image of the Antarctic ice sheets. You could imagine building a digital twin of Antarctica or building a digital twin of Greenland, again, to help model the changing properties, the changing state of those ice sheets, and again, using it to drive better decision making. So we have a physical system. We have the virtual representation. So what is the virtual representation? At its core, and I'll talk a little more about this later in the talk, but really it's a mathematical model encapsulated with some kind of numerical model. So it's a digital representation, a virtual representation of that physical system. And again, if we think back to that definition on the previous slide, the bidirectional interaction, the interaction between the physical and the virtual are really central to this idea of digital twins. We've had virtual models of systems for many, many, many decades. What a digital twin does is go beyond just having a computer model of a system and says, let's have that bidirectional interaction. Let's think about the flow from physical to virtual. So this is where we're collecting data or making observations of the physical system and feeding those data, those observations, into the virtual representation. Mathematically, this is what's called an inverse problem or data assimilation. There can be sensor fusion, there can be model adaptation. And this process from physical to virtual is where we first personalize the virtual representation. So it's not a generic brain and a generic tumor, but it's rather one personalized to a particular patient. And it's also the process by which this virtual representation becomes living, really becomes a dynamically changing model that's following the physical system through its life. So that's the flow one way, but remember we've got the bidirectional flow. So the second, or the other direction, from virtual to physical, this is where we're now taking this personalized, dynamically evolving virtual representation and using it to drive change in the physical world. And how do we drive change in the physical world? Well, it could be through control on board an aircraft, or if you like to think of an optimized treatment plan as a control problem. Could be just generally through some kind of decision making, maybe that doesn't manifest as a control problem. It could also be through changing the data that we're collecting by moving sensors around or deciding to put sensors in a different place, deciding, for example, where we might want to invest in drilling ice cores in the Antarctic ice sheet so that we get data in the future that are going to better inform the virtual representation and ultimately drive the decisions. And I think you can get a sense with all these examples I'm giving you that it's not one and done, but this bidirectional flow is really this back and forth, this continual back and forth from the physical to the virtual, back to the physical to the virtual. So these are all really important ingredients of a digital twin. We're not quite done. There's a few more. Validation, verification, and uncertainty quantification. Really, really essential pieces of a digital twin, because it's not enough to do all this updating and making predictions. If we're going to drive critical decisions about people's medical treatment or decisions about engineered systems like aircraft or autonomous vehicles, we need to know how good these models are. And again, it's not going to be once and done, but this validation, this verification, this quantification of uncertainty is going to also need to be done continually as the models are getting updated. And then finally, while there are some applications of digital twins that will be fully automated, there are probably many more applications of digital twins where there will be humans in the loop. And the humans might be in the loop as the decision maker. So think of the medical examples. I said think of a future vision. Maybe one day we'll have digital twins making the decisions in a fully automated way. More likely we will have digital twins as assistants to human doctors. So a human in the loop for the decision making. The human could also be guiding the sensors, could be interpreting the information. So this notion of human digital twin interaction also a really important ingredient of a digital twin. Okay, so many pieces of digital twins, and of course mathematics and statistics are absolutely everywhere in this picture. The word math shows up over here in the mathematical model, but of course it underlies pretty much all those methods that go back and forth there between the physical and the virtual representation. Huge role for mathematics and statistics and digital twins. Okay, so I think it's really exciting. There is almost not a system that you could think of where you couldn't imagine, wow, wouldn't it be kind of neat if we had a digital twin of that? Maybe some of you have already got your favorite things in mind, and you could imagine, wow, imagine if we had a digital twin. Digital twins, I think, really have a huge potential to revolutionize decision-making across so much. I'm just going to show you a few of the pictures. These are examples from the Oden Institute. This is the big institute that I direct in Austin. So this picture up here, advanced manufacturing, as we think about manufacturing facilities of the future, the notion of having a digital twin making control at the process level all the way up to maybe at the level of a full fabrication facility. This is something that has got a ton of interest, especially as we're thinking about next generation semiconductor manufacturing and reinvesting in some of that infrastructure. In my own group, we've been doing quite a lot of work on digital twins for unmanned aerial vehicles. My colleague Marie Bajar is an expert on space junk, thinking about a digital twin of Earth orbits. Probably you've read in the news the growing problem that we have of more and more stuff being up there, not really knowing what's up there, not knowing what state it's in. So thinking about a digital twin that could be a dynamic living model of Earth orbits that could again drive decision making. So these are all examples from engineering. If we look at the earth sciences, the geosciences, I've already mentioned digital twins of ice sheets. So that's Omar's full-scale continental model of the Antarctic ice sheet. This visualization here, it doesn't render too well with the lights on, but this is a beautiful visualization from Patrick Heimbach's group that is modeling the interaction of the Greenland ice sheets with the Atlantic currents, and particularly looking at the effects of the changing temperature and salinity and properties of the ocean and the ocean currents and what change that has. And again, I think you could imagine if we had digital twins of parts of our natural environment, just how that could help us to drive better decision making around climate change. And then finally in medicine, I've already talked a little about the applications in oncology. Again, there's a huge, huge interest in digital twins for oncology, particularly because there's so much variability from person to person, and each one of us will respond differently to treatment. Each one of us will see disease progress in our bodies in very different ways. And then finally, in our Willison Center, this is focused on cardiovascular applications. Again, this is an example where you already are seeing digital twins making a difference in terms of personalized decision making around interventions for heart disease. So super, super exciting to think about all of these. Okay, so hopefully I've painted this beautiful rosy picture and you're all really excited, and then you say, okay, Karen, this is great. Where do I get my digital twin? So it's really exciting to think about this future, but it's also really important to recognize that we can't do most of this yet. There are examples, and I've mentioned some of them, the aircraft structural health monitoring, the aircraft engines, some early successes in hearts. But for the most part, we cannot, we're not even close to being able to get a full digital twin at the scale of all of Antarctica or for a complex advanced manufacturing facility. So let's think a little bit about what some of the challenges are and why this is a really tough problem. So first off, we need a way to conceptualize a digital twin. And I don't know, maybe I've already primed you all with what I've said, but if I were to stop somebody on the street and say, digital twin, really exciting, what's the first thing that comes to mind? What do you think of as being at the core of the digital twin? What do you think they might say?
Privacy.
Privacy? Well, that's okay.
Similarity to us.
Similarity to us? Yeah. What makes a digital twin? What would you put in the middle? What would you put in the core? A computer. Yeah. Say it again.
A computer with data.
A computer with data. I think a lot of people, and a lot of what you read in the mainstream kind of media, digital twins are built on piles of data with computers. Yeah. And maybe privacy is a closely sort of related topic here. So this is certainly one way to think about a digital twin, that we have tons of data. We're going to wrap some kind of a numerical model around that data, and that numerical model is probably some kind of a machine learning model. Increasingly, when we have piles of data, it may be interpreted through the lens of a machine learning model, or it could be a more classical statistical model with enabling some kind of analytics and eventually driving decision making. So I think this is a fine and valid way to think about a digital twin. And in fact, when you look at where some of the biggest successes of digital twins already exist in society, they are problems where this conceptual view of a digital twin works really well. And one example is the health monitoring for aircraft engines, where the aircraft engine is generating tons and tons and tons of data every time it flies. That data is being sort of dumped down after every flight. So you've got piles of data, and the decisions you need to make are actually relatively simple in the sense that they're decisions where the data are very expressive about what's going on. They're decisions about when to do maintenance, when to take an engine off a wing. So there are decisions that really fall well within the realm of all the data that you're collecting across all of your fleet. So this is a fine way to conceptualize a digital twin, but this view of a digital twin with the data at the center is not sufficient for many complex systems, and I want you to think a little bit about why that's the case. So all the examples I've been giving, whether it's evolution of a tumor in a person or what's going on board the structure, the wings of my aircraft, these are complex physical phenomena. They're multi-scale, multi-physics, right? Just think about the human body. We know that things, when changes at the molecular level, at the very, very fine level, cascade across scales to have impact on us as human beings at the full scale human level. The same is true in engineering systems. So many, many scales, nonlinear interactions. When we start thinking about digital twins of these complex systems, we're going to be talking about parameter spaces, state spaces, decision spaces, where there could be thousands, millions, maybe even billions of variables. I mean, just think of all the variables you would need to describe something like the Antarctic ice sheet. So very high dimensionality. The data, yes, in some cases we do have lots of data, but for many, many, many more cases, the data are actually very limited. First of all, the observations tend to be noisy, they're indirect, and they're expensive or intrusive to acquire. What does that mean? So if I'm trying to collect data about the health of the structure on my aircraft wing, I don't get to break open the wing and see what's going on inside. I have sensors on the outside of the wing, really noisy sensors, and I have to take those measurements and try to guess or try to infer what is happening on the inside. So the data are indirect. The same is true in medicine. Doctor doesn't get to kind of open you up to see what's going on inside. Those images are images taken from the outside, trying to infer what is going on the inside. And while imaging technology sensors have really progressed, we're still limited in the data that we can collect. And that last point there, expensive, intrusive to acquire, if you have somebody who's sick, you can't make them come in every day to get imaged. You saw how infrequent those MRIs were in that example. If it's an aircraft wing, every sensor that I add on board the aircraft adds weight to the aircraft, it adds cost, and it consumes power when the aircraft is flying. And so this is true sort of across engineering systems. Yes, we have a lot of data, but the data really are limited and are expensive to acquire. And then the last one, verification, validation, uncertainty quantification. I already talked about that one when we saw the figure. Again, this is a huge challenge. Yes, maybe we could build digital twins of some of these complex systems today, but if we don't know how good they are and how much we can trust them, especially when we're making predictions about things that haven't happened yet, then we're really not doing anything that is particularly useful. So some really significant challenges related to issuing predictions for complex systems. So putting all that together, yes, we have a lot of data, but big data alone is not going to be enough for many, many cases. which means that our digital twins really have to think about embedding our domain knowledge, our knowledge of the science, of the governing equations, the predictive power, the interpretability that mathematical models bring. And when we say mathematical models, what do we mean? We mean things like F equals ma, right? The governing equations that you all learned in high school. F equals ma is the governing law that says if you hit an object with a force, here's how it will respond. Here's its motion. And we have more sophisticated models. They often come to us in the form of differential equations that, again, are governing laws that tell us if I were to do this to a system, how would it respond? And often these mathematical models are imperfect. They're imperfect abstractions of reality, but they're still very, very powerful in encapsulating what we know about a domain and about letting us make predictions for conditions that we haven't seen yet. So let's come back to this conceptualization of a digital twin. And again, the data-centric view is absolutely valid in some settings. But for many settings, we really have to be thinking about the mathematical model, the governing equations, the physical principles, the domain knowledge as being absolutely the core of the digital twin. Around that is wrapped some kind of a numerical model. So now this numerical model is some way of solving on the computer these sophisticated mathematical models. Then we bring in the data. So the data are coming in. The data still play a really critical role, but the data are now being assimilated through the lens of the models. The data are informing the parameters, the initial conditions, the boundary conditions, the parts, maybe the parts of the system that the model doesn't capture. The data are coming in and being interpreted through the lens of the model, and then decision making wrapped around all of that. So really two ways to think, data-centric and a model-centric view of digital twins. And if we want to get to the point of having digital twins for all those really exciting applications that I started with, this view on the right is absolutely something that we have to progress. We have to progress the mathematical and computational methods that let us have this model-centric view of a digital twin. Okay, so now I'm going to tell you just a little bit about some of the work that my group has been doing over the past few years. And again, I'm going to try and do this without equations. One of the things that we've been doing is to use what's called a probabilistic graphical model as a mathematical foundations for digital twins. So probabilistic graphical models are used in robotics. And if you want to think about fields where this idea of a physical and a virtual and this interaction really has a long history, robotics is a great example of that. I'm going to spare you the gory details of how a PGM, a probabilistic graphical model, works, but I do want to give you a sense of how do we go about thinking about a digital twin, thinking about it in a mathematical way, and then building scalable numerical methods on top of that mathematical abstraction to actually create a powerful digital twin that we can use to make predictions that we trust. So the first thing we do is to try to formulate the digital twin, meaning we want to find a way of sort of defining the digital twin. And the way we do that is we think, first of all, about defining these three different types of elements that you see here. And these are all things that live in the physical world. So first off, we have the notion of state. So all the things, all the variables, all the attributes of the system that I might want to track. And you can imagine just how many of these things there might be. The observational data. So what is the data? What can I collect about my, it says here, asset, about my aircraft? So I might have sensors on board a wing. I might also have flight logs. I could have all different kinds of data that I can collect. And then the control inputs. What are the actions or the decisions that I can take to influence the physical system? And these control inputs, again, these could be moving surfaces while the aircraft's flying to change the way that it flies. Or these control inputs, these could also be decisions that say you need to install another sensor, or you need to take the aircraft off to have an extra inspection. So these could be decisions that influence the data that we're going to collect in the future. So these three quantities, the controls, the state, and the observational data in the physical world. Now in the digital world, we're going to define a digital state. So this is going to be the way that we are representing all these millions and millions and millions of things we want to track about the system. How are we going to represent these things in our virtual models? And by the way, this is where our physical models, our mathematical model really plays a big role, because it's what lets us represent the digital state in a computationally tractable and manageable way. We are going to define quantities of interest. What are the things that you would like to predict? What are all the things that you can't measure, but you would like to be able to predict, especially the things you would like to be able to predict about the future? So for example, you might want to predict what's the maximum stress that's going to happen on the wing, because you want to be sure that whatever you decide to do with your aircraft doesn't exceed the stress that the wing can handle, because you don't want to break the wing. So again, quantities of interest, things you would like to be able to predict. And then finally, this notion of a reward, which says, how do you know if a decision is good? So this could be related to the performance of a system. How well does my aircraft execute its mission? It could be related to cost. How much does something cost? Could be related to environmental impact. And more likely, it could be many of these different pieces that have to go together to quantify the costs and the benefits. Okay, so we take all those elements, we feed those in, we create a probabilistic graphical model. We basically are thinking about the digital twin as a graph, mathematically, a graph with all these pieces connected. And then we can start using it in some of these examples that I've been giving you. So I will show you an example for an unmanned aerial vehicle. So it's one of these, you'll see it in a second, a Telemaster unmanned aerial vehicle that I have in my group. And with this sort of idea of representing the digital twin as a graph, we're now going to go through the process of building, first of all, creating the digital twin. So going and taking measurements of the geometry, because not every aircraft is built exactly the same, and we need to calibrate the geometry, so this model is going to be personalized. We're going to need to calibrate material properties. Again, not every piece of material that comes out of the manufacturing facility is the same, so we want to calibrate the material properties to build a personalized model. Calibrate mass and damping. These are all parameters in our digital state. Once we have a calibrated digital twin, we now would like to use it in the example I'm going to show you for dynamic estimation of structural health, meaning that this unmanned aerial vehicle is flying, it's got sensors on board the wing, the digital twin is constantly acquiring data from the sensors on board the wing, and if something happens, this wing gets damaged, the digital twin is going to be able to assimilate that data and then help the autopilot make decisions about how to fly the aircraft safely. So I think, oh yes, so here are some pictures of the vehicle. So this is the vehicle. This is actually the vehicle at its first flight in Massachusetts. We designed and built this thing when I was still at MIT. The vehicle is now in Texas. If you can see, you can kind of see this mess here. This is all the strain gauges on the wing. And again, I really want to emphasize the point I made earlier, which is everybody talks about big data. And sometimes actually I talk with people who work in the medical field. I talk with doctors and they say, oh, you engineers are so lucky because you can measure whatever you want. That's not that way in medicine. Well, it turns out in engineering, you cannot measure whatever you want. We are stuck with these strain gauges. I don't have a picture of it, but wires everywhere, giving really, really noisy measurements at a few locations in the wing. You can see here also the wings set up and the bench in the lab for some kind of benchtop testing. And then the last part of the story is that I had a PhD student who needed to finish his thesis, And when COVID hit, the labs on campus got shut down, and so the UAV had to come home to my garage in Austin. And then we had to put my then middle schooler to work collecting data from the strain gauges. So, all right, so I said 20 foot before, a 12 foot thing. Okay, so that's the physical counterpart. So now the virtual models, and again, this is a setting where we really think about the models, the mathematical models, as being the core of our digital twin. Our models are built on finite element structural models. So this finite element method is the workhorse of structural analysis. It has literally contributed to the design of everything that is around us, everything that you're sitting on, everything that you will touch, all the bridges that you will drive over on your way home. So incredibly powerful predictive model. We worked together with a small company, Excelos, that was several years ago a startup out of MIT, to create what are called reduced order models, meaning that while these finite element models are incredibly powerful and predictive and fast, they're about a minute for an analysis. That is way too slow if we want to run something on board a vehicle. So we have a whole bunch of other mathematical stuff that we do to these finite element models to create reduced order models that run really, really, really fast, so a fraction of a second to be able to run on board the vehicle. The other part that is kind of interesting mathematics is that we don't try to create a digital twin of the whole aircraft, but what we do is to decompose it. We break it up into pieces, and we mathematically model the pieces independently, and also use some theory to model how each piece relates to each other piece. And that's really powerful because what it lets us do is when we get data while the aircraft is flying, and let's say that we get some data that something is going on in this particular panel here, we don't have to update the whole model. We can update one piece of the model and then propagate the changes through, and that makes for a really, really rapid update set. So again, lots of math that goes on in here. This notion of decomposing a complex system, being able to operate on the pieces, a really important part of a digital twin. So let me show you this is sort of a simulation just of how it would all come together. So if you first look down here on the left, you've got an aircraft. It's flying around these buildings. And when an aircraft flies around a corner, you will know that the force is going to push out. The tighter the corner you turn, you've experienced this as you're driving home aggressively in the wet roads in Sydney. The tighter the corner you turn, the more G's, the more load you are putting on the structure. So the aircraft is flying, and it's got two options. It can fly this aggressive route with tighter turns that'll get it to where it's going faster, or it can fly this more conservative route that takes longer, burns more fuel, but does not put as much load on the structure. As the aircraft was coming around here, there was some damage that got incurred on the panels, the two panels that you see here that are going in red. So as the aircraft is flying, if you look up here, what we're showing here is strain data being collected from, in this case, 3 sensors on board the wing. So right as the aircraft comes here and the damage starts, these sensors are going to now be collecting data that to the mathematical model will indicate that something is going on. All of that's getting fed into the digital twin, and then ultimately what ends up happening is right here the digital twin says, hey, you can't take this aggressive path anymore, you're too damaged. If you try to take this aggressive path, you're going to exceed allowable loads for your damaged structure, so you need to switch to the more gentle path. Okay, and so again, models, data, predictions, all data assimilation and updating, driving decision making. Okay, so that's kind of exciting. That work is several years old, and makes sense because I'm an aerospace engineer. What's really exciting is that when we started with this work and we started with this approach of abstracting the digital twin and representing it as a probabilistic graphical model, and this is work with Michael Kaptein, my PhD student, who actually also happens to be from New Zealand. We started with that mathematical abstraction because we said we really want an abstraction that would apply to many systems, not something that's just specific to an aircraft. And so a few years ago when I moved to Austin, we started collaborating with the oncologists, with the Center for Computational Oncology at the Oden Institute, and also with clinicians at MD Anderson Cancer Center, which is one of the big, really prestigious cancer centers in the US. And they said, hey, we saw your work on structural health monitoring for aircraft. What do you think about applying those ideas in building a digital twin for a cancer patient? And this is where I think mathematics is so incredibly beautiful, because I thought, okay, it'll be a little bit of work to bring things over. Turns out everything that we had done for structural health monitoring of the aircraft wing just sort of ported over so beautifully to the cancer patient setting. So you remember these quantities that we had before. So the physical state, before I was thinking about the state of the aircraft. Now we're going to be thinking about the state of the human patient, their anatomy, their morphology, mechanical and physiological states of the material. I call them material. I'm sorry, I'm going to use engineering terms for, I don't know if we have any doctors in the audience. The tissue properties, and again, we have observational data, and just like in the aircraft example, we could have onboard sensors, or we could have flight logs. We had a lot of different sources of data. Same thing is true in medicine. Lots of different tests, images, different sets of observational data that can be taken. And by the way, just like in the engineering example, the data indirect and they're sparse. And what's really interesting about the medical examples, in engineering, we often have sparse in space. In medicine, the observations are very sparse in time. You're trying to model a dynamical system that's changing in time, but you're getting images like once a week or once a month. So very sparse in time, very, very interesting mathematical problem. Control inputs, and again, just like in the aircraft example, the control inputs could be the controls, the treatments, but they could also be the decisions to go and take another image or to take a biopsy. Then moving to the digital world. So again, we have a digital twin state, and again, we are defining the digital twin state through the lens of these mathematical models. One of the things I was fascinated to learn was that the models, the mathematical models for tumor dynamics are reaction diffusion models, which actually are not too dissimilar from the reaction diffusion models that I work with when we work on rocket combustion. The dynamics are very, very different, but again, the sort of universal language of mathematics with these partial differential equations. So we have digital twin states. Again, we have quantities of interest. What is it that we want to be able to predict about what's going to happen in the future? And then lastly, we also need this notion of reward, which is not just the patient outcomes, but also things like toxicity. How sick does the person get along the way? And how are you going to maybe limit the dosages that you give? So just like we did in the aircraft example, we can think about all these steps. Again, we're taking the mathematical models, we've taken this abstraction of the different kinds of data we have, the predictions we want to make, how we're going to measure what's good. We build this graphical model that really is representing all the pieces, and we can now think about calibrating initial conditions of the tumor, calibrating the tumor physiology, calibrating the response of the patient to the radiation therapy, and then using the digital twin to do dynamic monitoring of the disease progression and also drive optimized therapies. So we already saw this picture, but again, just sort of coming back to it now in the context of the example, this is the specific setup that we've been considering together with the oncology experts, where again, we've got an MRI at day 0, another MRI at day 20. The standard of care for the first week, we're using an extra MRI in here, and we're using this because we're calibrating the patient's response to the radiotherapy treatment. And then out here, now this patient-specific optimized radiotherapy regimen. I'm going to show you a few results, and it's, I don't want you to be overwhelmed by looking at, maybe you like looking at distributions, statistics, but just to emphasize that, and this is something else that I've learned about the medical examples, uncertainty drives everything. Uncertainty and variability drive everything. So what we're looking at here are the priors. Before we take any measurements, this is our guess, our estimate of these key parameters. These are the key parameters that are in those mathematical models. And these priors, these distributions, come from actual patient data. And so what this says is that my proliferation rate, your proliferation rate, any of us in this room, could be anything on this spread. Same thing for the others. And you say, okay, well, that's fine. I don't really know what they are. Is that a lot of uncertainty? So we could take these distributions and we could push them through the model. And we could say, if this was the initial tumor count, and then the tumor grows, and then the tumor comes down as we're delivering the radiotherapy, and then we stop the radiotherapy, and then at some point the tumor is going to start growing again. What we're looking at here in the blue shaded region is the uncertainty that results from taking these patient populations and pushing them through the models. So what it tells you is that if you just take all this, push it through, you have no idea, right? It could be down here, could be up here. Here's the mean, but I can guarantee you none of us in the room would be the mean. So this is an example where the variability, because we are all different and there's so much uncertainty in this problem, drives everything. So I think it's an example where this idea of a digital twin can make a huge, huge difference, because treating the standard of care, treating to the average, is not going to be effective probably for anyone. So now what are we looking at? We're looking at the post areas, which says the blue is what you started with by just looking at the population of data. Now collect data, and I should say these are virtual patients, so we're not looking at anyone's particular data. These are virtual made-up patients. But we take the data from virtual patient 1, and now here's our estimate of their proliferation rate, their other parameters. You can see there's still a lot of uncertainty. You can see that actually the data tell us practically nothing at all about this model parameter. But we have learned something about the other parameters for patient 1. And if we now take the posterior, take the yellows, and push them through the model, then this is what we get. Again, there's a lot of uncertainty, especially as we get out here, as to when and how quickly this tumor will come back. But you can see that the uncertainty has been considerably reduced by bringing in the data. So let me flick through a couple of patients, patient 1, patient 2, patient 3. And again, what I really want you to notice is just how much variability there is between patients. So again, there's just the response is so very different. If you talk to a clinician, they will tell you, they repeatedly say cancer is not one disease. It's so many diseases. So again, it's really exciting to think about what the mathematical modeling, the digital twins, could do in this setting. So again, we won't go too much into the details, but let me show you just these results. This is an example, and I should say that the first work we've done, we've used a very simple model. We are working right now on the more sophisticated partial differential equation models of the tumor. This first work is with a simple ordinary differential equation, a lumped parameter model. But these are examples of the kinds of results you could imagine giving to a human doctor, which is to say we're plotting here the time to progression, and we're using what's called a superquantile. We're actually not looking at mean behavior. We're actually looking at tail behavior because we're concerned about risk. But this is some measure of the time to progression. How quickly does the tumor come back above a certain level? So we want this to be big. We want to delay the return. And here is the total dosage. And we want the total dosage to be small because the more radiation you give to a person, the sicker they get during treatment. And what we're looking at here is the Pareto curve that says if you want a total dosage of 40, here's what you get for time to progression. If you're willing to up the dosage to 60, you can increase that time to progression all the way up to 100, which is an unreasonable dosage. You could really push it out. And we see now the Pareto curves for 3 different patients. Again, they're different because these patients respond differently to the treatment. And the last thing I really want you to notice is here's the standard of care. And what this tells you, again, simple model so far, is that we can always beat the standard of care. You can either get the same time to progression with a lower dosage, which means same outcome, but less harrowing treatment, or for the same total dosage, we could get a longer time to progression. So again, I don't want to emphasize the results too much because the model's very simple, but again, this is, to go back to that first picture, this idea of a digital twin assimilating the data through the models and ultimately providing this kind of guidance to a human decision maker to help them make better decisions. Really exciting. Okay, so to close, digital twins, really exciting, but I want to emphasize something I said earlier, which is so many of these use cases, despite what you might read in the news sometime, we can't do them yet. We need more math. We need more computing. We need better algorithms. We need better uncertainty quantification statistics. Really is a grand challenge that builds on mathematical modeling and computational science. One of the things I love about working on digital twins is that it is end-to-end, so many different pieces, and I have just some of them up here in the graphic. The way it puts together domain knowledge, really the physics and the science, or the medicine, the biology of what's going on, together with our favorite numerical methods, our favorite mathematical methods, uncertainty quantification, optimization, and control. Thinking about the computing, some of what we're doing is really high-performance computing where we're running models offline ahead of time. But this notion of edge computing, what kinds of computations can you do on board of the aircraft or in the clinic because the doctor wants to see a what if right in the moment when the patient is there. And then all the other pieces. And of course, AI and machine learning also needing to play a really big role. So with that, I will stop. Again, thank you all for braving the weather and sticking with me, but I'll be happy to take any questions. Thank you.